Hello again, young Laker physicist. Today's video lecture is going to be on thermal energy, heat, and temperature. Those words a lot of times are used synonymously, and we don't necessarily think about the differences or the exactness, the precise definition. Today we're going to iron those out and hopefully be able to use them going forward. So what's the connection between them? What's the difference? Things you're going to want to key in on in this lecture are going to be: what is thermal energy? What is heat? What is the significance of the absolute temperature scale? Lots of scales out there. How come I'm going to insist you use just one? And how do you convert from degrees Celsius to Kelvin? Right? So we're going to start with a little bit of a history lesson. Early on, what made something hot or what made something cold was a bit of a mystery, and it was actually a source of a lot of research and debate. One step forward was made by a man who is pretty famous in science, Antoine Lavoisier, who is famous for sort of becoming the father of modern chemistry. He advances the idea that mass is conserved in a chemical reaction. Matter can't be created or destroyed. He advances something called the caloric theory of heat. And ultimately, we know it's going to be wrong, but some of the things that he said have stuck around instead and stayed in modern thought and nomenclature. An interesting thing about poor Antoine, he was a nobleman, a tax collector. He was ultimately beheaded during the French Revolution. It seems the masses don't like their money taken every time they enter Paris for the king. For Lavoisier, he thought that what made something hot or cold was something flowing into or out of a substance or matter. He called this thing that flows in or out of a substance, he called it the caloric. That was a substance to him, and he actually believed it. It would be like an element, like anything else. So on a modern periodic table, if Lavoisier was right, there might have been a box called the caloric, and the caloric was responsible, the absence of caloric or the excess of caloric, for making something hot or cold. So liquid water was hydrogen and oxygen plus caloric. If caloric flowed out of it, it would become ice. It would still stay hydrogen and oxygen, but ice would be water minus caloric. So caloric to him was a substance that could flow out of something and make you cold, or maybe it could flow into something and make you warm. We know today that there's no such thing as the caloric, but it is the root word of calorie, which sticks around, a unit for heat or thermal energy. And we also still talk about heat flowing because of Lavoisier, although it's not a liquid, nothing's actually flowing, but it did stick around. So Lavoisier's idea was ultimately disproved by a famous scientist who went by the name of Count Rumford. Count Rumford is definitely less scary than Count Dracula, less delicious than Count Chocula, but he was a very, very smart man. He had a kind of a boring job, though. He was in charge of watching cannons be bored to make weapons. And what he noticed was there was an enormous amount of heat generated when this happened. And what his insight was to actually connect the bore and put it in water. And he noticed that as long as the bore was spinning and rubbing against the cannon, heat was produced. The water kept getting hotter. So if caloric theory from Lavoisier was right, it would mean that somehow this fluid is endless, it's infinite. But what Rumford ultimately says is no, there's no such thing as the caloric. Heat, or what we know as something getting hotter, is actually a measure of motion. As long as we have this cannon being bored, something's moving, we're producing heat. So although Rumford hasn't produced our modern theory of heat, he is one of the first to connect it to the idea that thermal energy and heat are going to be related to motion. And today we know that his ideas are right, and we've progressed them a little bit. Thermal energy, we know today, or we say today, is simply the total kinetic energy of all the atoms moving in a substance. So if we could shrink down and measure the velocity of all these little atoms, right, and do 1/2 mv squared for each one and add them all up, we would come up with this idea of thermal energy. So something that we say is hot or has a high thermal energy really just means that all of those particles together have a lot of kinetic energy added up. Something cold, all of the particles are moving slower and they have less thermal energy. So just think about thermal energy as the collective kinetic energy of the atoms in a substance. So what is temperature actually a measure of then? It can be kind of mysterious, right? You put a thermometer in and it reads a high or a low temperature, but what thermometer is actually measuring is the average kinetic energy of all the atoms or the molecules that make up the substance. Some particles are moving faster than others, some are moving slower, so it is a measure of the average energy. But you can imagine these particles collide, they hit the thermometer and they transfer some of that kinetic energy in, and we can actually ultimately see that transfer of energy by an increased temperature reading. So in short, the faster the atoms move, the more kinetic energy they have, the higher the substance's temperature. So we've built thermometers and had temperature scales for long periods of time, well before we knew that we could tie this idea of thermal energy to the motion of the particles that make the substance up. Some real common ones, of course, are Celsius and Fahrenheit. But it also tells us, if we understand the history of it, why we use that word degrees Celsius or degrees Fahrenheit. Celsius had a pretty good idea. We find something in nature that happens at the same temperature everywhere, every time. Celsius says, hey, water always freezes at this temperature. He calls that 0 degrees Celsius. Water always boils at the same temperature, so he calls that upper end 100 degrees Celsius. Chunks everything into 100 in between. That's why sometimes the scale is known as centigrade. Fahrenheit, though, a little bit strange. We use it in the United States all the time, but what was he basing it on? He was basing his 0, which would probably be somewhere like right around here, basing that 0 on a mixture of salt and ice water, so below freezing temperature, and his upper end, which was about 98.6, what we know today, close to 100 Fahrenheit, was the temperature of the human body. So he used those as his benchmarks. The problem with using these scales is we know things can get really, really cold, a lot colder than this. We could have a very cold weather in the negative 90 Celsius, negative 128 maybe on the poles during winter. There's a problem with that, as we're going to see. If temperature is a measure of the speed or the motion of particles, what does a negative temperature imply? Does it imply a negative motion? There is no such thing. You're either moving or you're not. So, but the words or the nomenclature have the degrees of how far are you away from a Celsius idea of cold. Well, I'm kind of so many degrees of separation from what he thinks is cold, or so many degrees away what he thinks is hot. So degrees is kind of a fuzzy term, and we're always saying how far from being hot or cold are we from these benchmarks. So if we take their work and we expand it and think a little bit about, well, okay, let's think about the idea that molecules are moving, and that's what temperature is actually measuring. If we slow them down, really slow them down, that means getting colder and colder, what would we see? Well, the molecules would stop occupying very much space. You could imagine them sort of, instead of zinging around and a lot of space in between them, you could imagine them starting to condense and sit really close to each other. So as the volume would drop with the temperature, we could also think about the pressure. Pressure is nothing more than the molecules colliding with the walls of their container. If we get it so cold that the molecules are moving so slow, they collide with almost no force, so the pressure would drop. And when we do this, we find that there's a theoretical low temperature when molecules stop. They stop exerting pressure because they're not moving. They don't occupy volume because there's no space between them anymore. And when we do that, we come up with this magic but important temperature, negative 273 degrees Celsius. That is the lowest temperature we could ever have, and we sometimes refer to that as absolute zero. It's negative 273 degrees Celsius. We no longer then want to use the idea of negative temperatures because there's no such thing as negative motion. So we call this a new temperature. We call absolute zero, 0 Kelvin. And if anything is warmer than that, it's going to have a positive temperature associated with it. So this is our new temperature scale that we're going to use. Why it's important is it's the only temperature scale that actually captures the idea, the physics of it correctly, that temperature is a measure of motion. Things are either moving, the particles that we're, temperatures that we're measuring, or they're not. If they're not, they have a temperature of absolute zero. If they are moving, vibrating, jiggling, moving left or right, spinning, they have some positive motion and they'll have a positive temperature associated with it. So the Kelvin scale is the only thing really that captures the fact that kinetic energy, collective kinetic energy, which makes thermal energy, is really the reason something is hot or cold. It also means when we speak about temperatures in Kelvin that we've gone away from this fuzzy idea of how many degrees separated am I from someone's idea of hot or cold. So when we talk as scientists about temperatures on the absolute scale, we don't say degrees Kelvin, we just say so much Kelvin. So when you go to a physics or chemistry party in college, and there's going to be lots of them, man, they're crazy. You don't want to do what this guy's doing. It's hot in here. What is it, like 310 degrees Kelvin? No, we just say it's 310 Kelvin because we're no longer talking about degrees of hot or cold. We're talking about motion, period. You're either moving a lot and you have a high temperature recorded on the Kelvin scale, or you're not. So finally, what is heat then? Heat and energy are always kind of this thought about being as the same thing. Heat, real simply, is a transfer of thermal energy into or out of a system. So if particles are moving fast and they collide with slow particles, we know the physics of it. The slow ones will speed up. They'll have momentum transferred to them. The fast ones in that collision would slow down. So that's all heat actually is a transfer of energy into or out of a system. So we could say then that heat flows out of a system. If particles slow down, heat flows out of it. If particles speed up, we say heat flowed into it. But really what we mean is a transfer of thermal energy into or out of a system. So a hot object cools down because thermal energy flowed out of it. The particles actually slowed down, but they warmed up the surrounding particles. So the cool particles, which were moving slowly, would have been sped up. This will happen if we have a system in contact until equilibrium is reached. So all the particles are colliding with the barrier with equal energies. All right? That'll be enough for us to move forward. Take that quiz then on the Google form right now.